We've just had the COP26 conference in Glasgow, which was all about addressing the consequences of committed climate change and through adaptation and mitigating future climate change by reducing greenhouse gases to net zero. Today's webinar is therefore very topical because it delves into two of the elements that come from the COP26 meeting. A little bit about how the Antarctic ice cores support our understanding of greenhouse gas budgets, past, present, and future actually, and how nations like Australia and the 195 other United Nations countries respond to the treaties that come as a consequence of the science to limit warming. It's my pleasure to introduce our two speakers for today. David Etheridge, Principal Research Scientist at CSIRO and Project Leader of the AAPP Ice Cores Project. David's research involves long-term changes in the greenhouse gases and ozone depleting compounds, and this research actually has been used in all of the IPC assessment reports through the full 6 cycles. He also investigates the use of atmospheric methods for quantifying emissions from energy production, like the fugitive emissions from coal operations. And the second speaker, it's my pleasure to introduce Mr. Rob Sturges. Rob is the General Manager of the National Inventory Systems and International Reporting Branch at the Department of Industry, Science, Energy and Resources. So Rob is a key player in understanding the national greenhouse accounts that are prepared by the department on behalf of the government. He's also a member of the IPCC task force on the Inventories Bureau, and is a United Nations Framework Convention on Climate Change lead reviewer for the national greenhouse gas inventories. So it's a great pleasure to welcome our two speakers today. And now let me hand over to David Etheridge. David.
Thanks very much. Sorry for that delay. So this part of the today's webinar is about the role of the atmospheric composition as measured both in the Antarctic region atmosphere, but also back in time using ice, the air enclosed in the ice sheets. The focus will actually be on the greenhouse gases, although of course we can look at a whole range of atmospheric compounds, including ozone depleters and so on. And the greenhouse gases, of course, because of their radiative force and their influence on climate. The record of any measurement of the atmosphere depends a little bit on the observational footprint that is being recorded. Now that can be a local influence, for example, an industrial site, a feedlot, a regional influence such as a city or a coal or gas energy basin, or even an ocean. And then at the larger scale, of course, the hemispheric or global observation. Depending on where the observations are being made, we can reflect the influence of those sorts of scales. Atmospheric measurements are typically top-down, so that's where atmospheric observations are influenced by emissions. By inverting those, by going through an inversion process, we can infer what the emissions were that caused those changes in composition. But there's interpretation required to quantify the emissions from different sources that might be in that footprint. And I'll give some examples today where we use isotopes, which are essentially a fingerprinting of source emissions, but also by going back in time, especially into the ice sheets, then we can go before the anthropogenic influence and look at how the natural system of the atmosphere operated. It's a very different approach to the complementary bottom-up inventory approach, which Rob will probably concentrate on more. And often they agree, but not always. And sometimes there's conflicting differences. So the focus really is on the Antarctic and Southern Ocean today, and that means that we have information from stations, atmospheric monitoring stations around the region, but leading, say, from the CSIRO Aspendale Lab, where I'm talking from today, through the Cape Grim station, and then into the Southern Ocean region through Macquarie Island, Casey and Mawson on the Antarctic coast. But of course, the shipboard measurements happening from the Investigator and soon from Nyina. And then, of course, we move into the ice sheet to obtain a longer term picture. And we do that primarily through, in the past, using, and hopefully still in the future, using a very special site called Law Dome, and that is very close to Casey Station and has some wonderful attributes for our atmospheric record. But elsewhere in Antarctica, we have the Aurora Basin North site. We will soon, we hope, have the Millionaire Ice Core, taking the record way back in time, and ice cores and firn air sites from other locations that we partner with around the Antarctic continent. And we also work with Greenland ice at the other end of the planet, and that can give a very complementary north-south picture of atmospheric composition. Just a look at the sorts of information or the places where we get the information from. A typical atmospheric station such as Casey, a little hut offset from the main station. I should also mention that the Cape Grim programs incorporated an air archive sampling project where air has been containerized since the late 70s. And we can go back and measure that when we find a need, or we have the technology to measure some of the new compounds that we know exist. And here is Paul Fraser, who initiated this program, sitting next to the late Sherry Rowlands of ozone hole and Nobel Prize fame. And then going back further in time, of course, is the ice core record, and that comes from air enclosed in channels and eventually bubbles in ice, and that takes us back through centuries and millennia. The first and probably most impactful policy outcome of this work is simply, or maybe not so simple, it was very hard to produce and took many decades of many agencies reflected there, and no doubt others, which is the greenhouse gases over the industrial period and before. And the three gases of interest are shown here are the three main greenhouse gases: CO2, methane in the second panel, and nitrous oxide, from a range of ice cores, primarily from the Law Dome record. And then in the top panel, the isotope of carbon-13 in CO2, declining as CO2 increases, and confirming that CO2 comes from photosynthetic origin, so therefore land clearing and fossil fuel origin. Now this has of course had a very powerful impact. They're climatically active compounds, they're anthropogenically produced, and it takes the atmospheric record shown there in the black symbols in the recent decades back in time to show that over that longer term period, which I haven't shown here, this is the largest and highest concentrations of probably 800,000 years. So this of course has had a very powerful impact, but it is also used specifically as the radiative forcing of models. So those data have been combined into, and other data, 43 greenhouse gases represented here, largely from the Law Dome ice sheet, then into the Cape Grim records and other observational records around the planet, to give a global representation of greenhouse gas forcing. Those gases combined into a CO2 equivalent, and as you can see here, the industrial period reflecting those contributions, of course, driven largely by CO2, but then methane and the other gases. And these have been, and the radiative forcing of those gases shown on the right-hand scale. Now, these have been compiled for the IPCC CMIP6 process. So Any modelers out there using simulations over this period are probably using our data, and they have been published in a number of forms for this purpose. And of course, when those models simulate the climate with the various forcings, we see the relative temperature effects of CO2, methane, nitrous oxide, and so on, the whole range of understood radiative forces, and the observed temperature here showing that we quite well understand that increase. We can also use the gases from pre-industrial times to see how the changes have occurred naturally. And an example here is using what I showed before, which is the CO2 concentration, but also the C13 trend in the bottom panel there, showing that there's a decrease in CO2 through this cool period called the Little Ice Age, and reflected in an increase in C13, also in the methane concentration, a cool period affecting the land. And that 1 degree cooling was traced to terrestrial uptake, taking it more CO2 out of the atmosphere through the carbon-13 signal, which is discriminated by photosynthetic uptake. The clincher here was a measurement of carbonyl sulfide, which confirmed that this was actually a cooling effect on the terrestrial biosphere. And from that, we could look at the sensitivity of the terrestrial biosphere to temperature. And that showed a positive or amplifying effect of temperature on CO2. So a cooler period drawing down CO2 into the biosphere, then the resulting warming after that, releasing more CO2. So we have a potential here of an amplifying effect of the order of 20 degrees that's 20 parts per million per 1 degree warming. And that's a coefficient which is important for future projections of carbon cycle models. Another example, and I'm only giving a handful of examples here, but this is a curious one, which is for a perfluorocarbon-14, CF4, very powerful greenhouse gas, very long-lived in the atmosphere. Anything that is released is effectively there forever. And we see from the concentration measurements at Cape Grim, leading back into the fern and ice, that the concentration has increased. Previously, it was assumed that all of this came from the aluminium industry. But going back to pre-industrial and pre-aluminium times, we see, in fact, there was a background level around about half the concentration of present day. Now, that's a useful policy outcome, but so is the development of emissions over the period of the industrial. And that's shown in a number of curves here. But if you focus on the green and then the red, you'll see the inferred emissions that caused this increase. And of course, they increased largely in the aluminium industry. A small blip here due to aluminium increased production during the Second World War, and a decrease since around about the 1980s, as the industry understood they were emitting this compound and introduced measures to change their practices. And that's a good news story, because if you look at the bottom curve, the aluminium has increased in its production, yet the emissions per production amount has decreased through this knowledge, and a powerful outcome. And now the industry is gaining from not just reduced emissions, but also from better productivity of aluminium. Now, I'd like to finish up by focusing on methane, the most abundant atmospheric hydrocarbon, powerful greenhouse gas. It has chemical roles which need to be understood. It's a relatively short lifetime, so an emissions change will result in an atmospheric change quite quickly. There's a focus on fugitive emissions and mitigation of those emissions, and that's been reflected in the IPCC at COP26, but also the Global Methane Pledge, which has now been, I understood, ratified. And by pursuing mitigation of methane, we can rapidly lead to a fairly significant change in atmospheric concentration and warming. The sources are here, But the main source of interest, which I'll show you today, is the total fossil source. And that is around about a third of the total. But the partitioning between the natural and anthropogenic fossil source is very poorly known. So that's where the information from the ice sheets is immensely helpful. We can go back in time to see when only natural emissions occurred and how much were they in the fossil sector. Now this result in the panel on the left came out a year ago or just over a year ago in Nature. And it looks at the increase of methane over the industrial period, the almost tripling in concentration, and then measures the carbon-14 and the carbon of the methane. And that is affected primarily by fossil fuel emissions, because fossil carbon has effectively no carbon-14. Just window out this increase here, sorry about that, the increase here, which is due to nuclear processes and also the involvement of the bomb pulse of carbon-14 into the methane cycle. So just focus pre-1950 so, and you'll see that there's been a decline down to 1950 as fossil emissions of methane have been released to the atmosphere because they reduce the ratio of carbon-14 methane. But then at pre-industrial levels, before the anthropogenic emissions, we see that the carbon-14 sits pretty much on the carbon-14 CO2 line, which is telling us that nearly all of that, effectively all of that methane is derived from CO2. It's not coming from thermogenic or biogenic processes deep in the crust of very old origin. That means that in fact the inferred natural geological source is negligible. It's between 0 to 5 teragrams of methane per year. The inventory and the assumed methane budget takes 40 to 60 teragrams of methane coming from natural geological sources. By inference, that extra methane, or that methane that is not now related to geological sources, has to be placed into anthropogenic fossil emissions and likely fossil fuel. So that's a significant result and has had a lot of focus on how good is the result here. The criticisms have been, well, there's a lot of measurements of geological emissions around the planet, and they combined show much more methane from geological sources than we infer from the carbon-14. And perhaps a paper that just came out saying, well, this demands close attention before we dramatically revise our understanding of methane emissions on the basis of a single method and 2 samples. And that's right, because the pre-industrial measurements came from 1 site and 2 measurements. One of the beauties of ice core work is you can go back to material and information in that material that still exists in the ice sheets. So we went, for a number of reasons, back to Lord Ohm in 2018. And we did 3 drillings there for large amounts of air for about 3 main purposes. And one of those was to get extra samples for this carbon-14 methane measurement. And here they are, the new measurements just being released, not published yet, but they are here in the diamonds, in the black diamonds, extending right through the record and showing very good agreement with the published data. So we would say then that the excellent agreement and the extra data confirm that result, that the anthropogenic, that the natural fossil emissions are effectively 0, and that the anthropogenic increase needs to reflect more fossil fuel, probably, emissions into the recent budget. And that is actually telling us that the recent anthropogenic fossil emissions account for around about 30% of the global methane source. This work that global result is reflected elsewhere in regional studies, where, for example, in the Surat Basin in Queensland, an inverse modelling study led by myself and Ashok Luha, published the result a year ago. And we found that there was probably more methane being emitted than the inventory that we used for the same region. Another paper since published says that mismatch could be even larger in the Surat Basin. And elsewhere around the world, we're seeing, especially in the US, reassessment of methane emissions from the US oil and gas industries, implying more methane being released than was previously expected in the inventory. So here we have a global result being reflected around the world in more regional studies. This work, so just returning to the global policy focus and national policy focus from this work, it's reflected, of course, and used heavily in the assessment reports of the IPCC, including the latest one. I haven't mentioned ozone depleters, but the ozone depleting compounds and their effect on stratospheric ozone is reported and driven by a lot of this work in the UNEP WMO scientific assessments of ozone depletion. And more locally, the state of the climate, which is a biannual report produced by CSIRO and Bureau of Meteorology. And a very powerful report locally. It'll get some million hits within weeks of its publication. And this work is frequently reported in those national reports. Outlook, there will be an increased need for atmospheric composition measurements. We are using the modern measurements against the background of the long-term atmospheric record that we find in the Antarctic, in the Cape Rim Archive, and in the ice sheet, to see how modern influences are changing the atmosphere. And they will include global emissions mitigation, we hope. We've seen it in the ozone depleting gas emissions. We hope to see more influence of mitigation in the climate gases. And then specific things like the future energy systems, for example, hydrogen economy. Atmospheric hydrogen, we have a very long record of that now. How will fugitive emissions of hydrogen from a substantial economy around the planet affect the levels of hydrogen and the atmospheric chemistry response? I'll leave it there. Thank you. And I think now Rob will follow on from probably a more regional perspective. Thank you, Rob.
All right, well, thank you very much, David, for the excellent presentation. Yeah, so Beckton's asked me to talk a little bit about the interface between global climate science and policy. It's a big topic. So I plan to talk about a couple of things. First of all, we'll talk about the international policy architecture. And secondly, I want to talk about the national greenhouse gas inventory that I'm responsible for. I'll be skating over a number of issues quite quickly, and I guess my aim will be to allow for questions at the end of the report. So hopefully there'll be questions at the end. Okay. So you will have all seen the publicity around COP26 in Glasgow just recently. And so what I want to talk about a little bit is about the way that science impacts the international policy architecture. So I want to start with the UN climate treaties. So the first treaty was the Framework Convention on Climate Change, negotiated in 1992. And the objective of that treaty is to set out Article 2, I think it is, stabilize atmospheric concentrations of greenhouse gases in the atmosphere. So already you can see that the great work done in Antarctica is the kind of work that needs to be done to provide the foundation for everything else that follows, and the foundation for helping us to understand whether the convention's objective can be met in the future. Now, the Framing Convention didn't specifically identify the level of dangerous interference, which is kind of written into the text. And I guess we have a statement of that in the Paris Agreement that followed in 2015. So the Paris Agreement was important because it was the first time that developing countries were brought into the process of mitigation, but it did restate the treaty objective as stabilizing. It's rather than stabilizing concentrations of gases, it was about limiting warming to below 2 degrees, well below 2 degrees above pre-industrial levels. So that means actually that a bigger role for science in the understanding of how the treaties are performing and whether the treaty objectives are being met. The second way that science has an impact on the international policy architecture is through the National Greenhouse Gas Inventory. So in my view, this was one of the more important commitments made by governments in 1992 in the Framework Convention on Climate Change. And in my regulator community, there is an old adage about needing to be able to measure emissions to be able to manage them. So the inventory is about, the National Greenhouse Gas Inventory is about monitoring emissions at a national level to help governments track progress towards their emission reduction commitments and to inform mitigation actions. So, and this is a chart showing the history of Australia's National Greenhouse Gas Inventory. So we have a reporting commitment from 1990 onwards. And so we have that time series set out in the inventory. I'll come back to the inventory in the second half of the talk. Now, based on those inventories, governments make commitments to mitigate and limit and reduce greenhouse gas emissions. Under the Paris Agreement, the government submits something called a nationally determined contribution. And Australia's nationally determined contribution, I'm sure you're all aware, is to reduce emissions by at least 26 to 28% below 2005 levels by 2030. The government has stated that this is like a minimum target, and in fact, the most recent emission projection put out by the government indicates that Australia is on track to surpass that minimum commitment. Of course, the government, as part of that national determined contribution, the government also announced that it would commit to reducing emissions to net zero by 2050, and that was set out in a resubmitted national determined contribution to the Paris Agreement during the course of the COP26. All right, so different governments have different commitments expressed in different ways, reflecting different circumstances and histories. But what if the collective action of governments is insufficient to meet the treaty objectives? So here is where science has another big input into the process. The Paris Agreement provides for something called a global stocktake to be undertaken. The first global stocktake will happen in 2023. And that's where there is an assessment about whether collectively governments are on track to meet the Paris Agreement treaty objectives. Now, the IPCC reports are a big input into this thinking, and you'll know that the Working Group 1 report was released in August. There are Working Group 2 reports on impacts of climate change and Working Group 3 report on mitigation of emissions, which are due for completion in early 2022. There'll be a synthesis report done later in the year in 2022 to complete the 6 assessment report cycle. And then, of course, with this input feedback fed back into government commitments, then, of course, governments are urged to increase the level of ambition. We've seen plenty of talk of this in the press. And so it's part of the design of the system that governments make commitments, more information is fed into the process, and then the system is designed to allow for governments to ratchet up their ambition, is how it's expressed. So it is a kind of a natural part of the process as envisaged by the authors of the Paris Agreement, that governments would make commitments, the government commitments will be reviewed in light of new information, in light of the science assessments, and then governments would have an opportunity to enhance their commitments over time. So that's the kind of the international policy architecture. So science certainly has a very big role to play in the framing of the treaty objectives and the assessments about the strength of government commitments and whether the treaty objectives are in line to be met. So now within that policy context, I want to talk about the national greenhouse gas inventory. So not to be confused with any generic use of the expression inventory or a bottom-up model. The national greenhouse gas inventory is a very explicit kind of set of modelling methods and assumptions that we set out in a 1,000-page submission to the UN every year. I'll just take you through a little bit about the national greenhouse gas inventory. And certainly science has an important role to play in shaping the way that the national inventory comes together. But just some pointers about the inventory. So first of all, it is a UN treaty commitment to do the national greenhouse gas inventory. It's not a science exercise. The government commits to report on anthropogenic emissions and sinks. And as David mentioned, sometimes that gets a little bit, it takes some interpretation, right? Because with the CF4, we always thought that was a purely man-made emission as a gas source. So, but apparently that's no longer the case. So that boundary is sometimes a little bit blurred, but certainly governments commit to an inventory of anthropogenic emissions and sinks. Individual greenhouse gases are aggregated in the inventory through the device known as the global wind potential, which is estimated by the IPCC. And as David mentioned, 1 tonne of methane is worth 28 tonnes of CO2. And finally, just to say that what we produce is a policy variable. We kind of want to send a consistent signal to policymakers about progress towards government commitments. So therefore, in the inventory, we probably place a bit more emphasis on the value of the trend in emissions, and a whole lot of volatility is counterproductive in sending a consistent signal to the government. So yeah, that makes it a little bit different to just a scientific exercise. Transparency is very important for the way the inventory is produced. So there are a lot of rules agreed at the UN. We have a high degree of transparency in the inventory methods and data. So we make an annual submission, 1,000 pages long every year, detailing the data and methods. The methods used in the inventory must be consistent with guidance provided by the IPCC. So you can see on the screen there's a hefty world of volumes of guidance that comes from the IPCC. So we are assessed every year by teams of experts assembled by the UN as to whether we meet the guidance provided by the IPCC. And in Australia, we've actually had 2 A&O audits as well in terms of how the inventory is put together. So a lot of external scrutiny. All right, so now just trying to give you an overview of the way the inventory comes together. So David did mention the idea of how atmospheric models are seen as a top-down approach to modelling emissions. The inventory is a bottom-up model of emissions generated as a byproduct of economic activity. So I've pitched here that there are kind of 4 different kinds of functions that we use. And and I'll just go through those just very briefly. So the first kind of function is what we rely on, is relates to fuel combustion for coal and gas in particular. We rely on the company analysis of inputs, fuel inputs, analysis undertaken in accordance with ISO standards and by NATA accredited laboratories. So that's one kind of model approach governed by the National Greenhouse Energy Reporting Act. For a small segment of emissions, we do direct monitoring. So this happens in underground coal mines. Every underground coal mine heavily regulated for safety reasons, and there's direct monitoring of methane in the mine shafts. So we can access that data through the INGA Act. And then for other parts of the inventory, essentially we have a model of emissions where the model is calibrated based on available empirical scientific literature. And this happens in parts of agriculture, for example, in the waste industry. And then the fourth function relates to the land sector. So for the imagery, we use a model which is known as FullCam. I'm not going to dwell on this right now, but just to show that it's a complex model. It's driven by detection of disturbance history of forests monitored through analysis of NASA Landsat imagery, the model is calibrated based on a lot of research done in Australia by the CSIRO and others. So just to flag some of the science contributors to, and you'll probably know some of these people, to the imagery. And in the beginning, the imagery was actually heavily shaped by Ian Galbally from Aspendale as well, and many other contributors. Most of those have worked in the CSIRO at one place or another, Data 61, Land and Water Energy Division, and so on. So just to try and indicate that a large part of the imagery models heavily shaped by input of CSIRO scientists and others. All right, I just wanted to finish with a few pointers about the top-down approaches to trying to understand the emissions that David mentioned. So, as I just explained, in the way we do our bottom-up modelling, this happens only very rarely and only in a kind of special case in the coal mines, and then actually that's an estimate of the methane going up the mine shaft rather than methane out in the valley. But one place where we have done some, or there has been some really interesting work is the Surat Basin that David already mentioned, where coal seam gas operations occur, methane released in that process. So the imagery does work on a very much a bottom-up basis, and it relies on a lot of studies trying to look at the leakage kind of rates that you might expect from different types of equipment in the field. And in Australia, there's only a small number of studies available to support the imagery. Stuart Day was involved in a lot of the work that we use in the imagery. There's more work happening right now in the CSIRO Energy Division to try and update and broaden the available data on leakage rates. And so in the absence of Australian data, we can tend to rely on data coming out of the US, where there's many studies being done on leakage rates across the gas industry in the US. So, well, given that we have limited observation base in Australia, what can we do about that? Well, David's study was very helpful. A top-down study, an independent kind of verification of the imagery methods, where flux towers are set up in the Surat Basin and trying to detect the amount of methane wafting down the valley. So although in David's study, they did compare their results with a bottom-up model prepared by consultants. Actually, it wasn't really a test of the methods used in the national inventory. And when that was done by the department, we found pretty good agreement between what the industry would say should be wafted down the valley of the Surat Basin and what David's study found. And last year, the University of New South Wales, funded by UNEP, did a different approach to trying to understand the shape and the magnitude of the methane plumes in the Surat Basin. So using aircraft to fly through the methane plume and to model track the plumes, and then trying to work out where those methane came from. We worked quite closely with the New South Wales University on the bottom-up side of the equation. And again, we got very, very good agreement between our estimates using the inventory and the New South Wales University funded by UNEP estimates. We do have similar kinds of things happen with relation to HFCs and SF6. So Paul Fraser, using data coming out of Cape Grim, does a similar kind of verification exercise on the HFC emissions from the inventory. So it's certainly a field where we feel like this is a really important avenue for getting testing of the inventory methods, ensuring the inventory methods are robust, and if we can't reconcile with the top-down approaches, seeing how we might improve things. Now, I did want to try to finish on some more ambitious kind of inverse modelling top-down approaches that are happening around the world at the moment, especially with the number of satellites circulating the planet and taking readings of greenhouse gas concentrations on a regional basis. So this is a paper that got some publicity during the COP26. Hasn't been peer reviewed yet, but it's still available. And it is kind of a sign that in the future, there will be lots more data coming forward from top-down models, which will present good tests for the robustness of the inventory methods that we apply. And this is a good thing. Do these tests provide a robust, do these models provide a robust test for the imagery yet? Well, I don't think so, not yet. So this chart is, well, the very steady bright yellow line there is actually what's reported in the national inventory across all gases and sources and sinks. And the two dotted lines represent the range of outcomes presented in this study, the field CA study that was released during COP26. It reflects the results of over a dozen inverse modelling exercises used by the Global Carbon Project, which is a really fabulous kind of initiative that Pep Canadell was very much involved in. But the totality of the results show a really wide range of outcomes for Australia. And that's something that's an interesting result, but does just show that there's plenty more work to be done to fine-tune these approaches going forward. I think I'm just about out of time, Nathan, but just to say that this kind of thing is really good exercise, is really valuable for the national greenhouse gas inventory, for improving the robustness of the national inventory. And I really do love that paper that David talked about in the Surat Basin. There will be plenty of challenges for the industry going forward from these kind of approaches, but I think they have quite a bit of refining to do before they can reach their potential. So on that note, Nathan, I would like to close up and offer time for questions.
Thank you very much, Rob. Those two talks were fantastic. And I've just asked Dave, sorry, I'm confusing my Davids and Robs now, David Riley to unmute, because we're not so many people. And if you like, please put some questions into the chat. I've actually put a few in myself, but I prefer the questions from the audience. Questions for either David and Rob. And if we can unmute while David Riley's unmuting everyone. Can we actually, participants can now unmute. So there you go. If you want to ask a question, put your hand up and unmute. And I'll just kick off because while people are getting ready. One of the graphs I saw there, Rob, kind of suggested that the underlying sectors was actually increasing, and then the purple colouring was actually declining, and this was how we were going to achieve the 20%, 28% reduction by 2030. If that was in your inventory figure time series. But there's upward pressure, I think, from other sectors. So what does that actually, does that have some implication for the challenge actually of meeting the minimum requirement of 28%? I'm wondering if you can remember the figure.
Yeah, so look, of course, the story of electricity is really important for the national inventory progress over time and the government's commitment. Emissions from the electricity sector peaked in about 2007. And that reflects, decisions taken over the previous 50 years for capital investment in power stations, particularly coal-fired power stations, places like Hunter Valley and so on. Going forward, of course, renewables are taking rapidly an increasing share of the electricity market, and those emissions will decline over time in the electricity market. And I think I'm right in saying is that we project that renewables will take around 50% of the capacity in the electricity industry by 2030, about 50% of the capacity. So it's a really rapid change in the makeup of the composition of the electricity industry. And that will drive it is the main driver to get to the government's 2030 target reductions in emissions from the electricity sector.
I see. So they're actually anticipating that transformation. So just to the audience, you can unmute and just ask your question or put your hand up. I have a sort of a second question, Rob. The full CAM model, I'm thinking that actually there's some potential across all those inventories for some level of biases and underestimating. And I think you've kind of answered it in the last slide where you showed basically the remote questions could, the remote sensing was still large enough in error and not to restrict. So the national greenhouse inventory looked okay relative to the estimates from remote sensing.
Yeah, when it comes to land, we have traditionally focused on the question, well, how is the carbon stock changing over time? And if it's changing more quickly over time, then that is essentially what we've tracked towards our target, because target's always expressed in the future relative to a base year. So how fast is the forest sequestering carbon in 2030 relative to 2005? And it's only the increase in the rate of sequestration that actually counts towards the government's target. It's true that from the inverse modelling exercises, there is an indication that the carbon sink in Australia is actually bigger than what we report in the inventory. The IPCC have confirmed that in their Working Group 1 report. And that question, when we talk about net zero by 2050, we're now talking about in absolute terms, right? Absolute terms rather than a relative change. And so we will be spending more time addressing this question around what is the absolute sink across Australia in future work.
It's kind of fascinating. So I see a question from Dan there, and actually I think it's really addressed to you, David. This question is, methane decays relatively quickly in the atmosphere. Is that a process that's completely halted in the ice core bubbles without a source of new OH radicals?
Yes, it is. So the the radicals that remove methane from the free atmosphere, primarily hydroxyl, but also chlorine radicals, are completely extinguished within the ice. So the storage of methane is actually very good within the Greenland and the Antarctic ice sheets, and even some tropical ice sheets where there have been measurements. And this is important because for almost all of the gases I think I showed, the ice stores and faithfully retains the atmospheric composition for millennia, and in some cases that's better than we can do in carefully treated containers and steel and glass flasks. We can't test that because we don't have such flasks so old, but we know that there's some of these compounds are sensitive to their storage medium. The ice is clean, very cold, very inert, and so we know from a number of tests that works for these gases.
Thank you, David. My audience here is being very, there we go, from Joel. Joel, do you want to ask a question by unmuting? I can read it out otherwise. So while Joel's unmuting, meeting Australia's 28% target includes a big contribution from the land use change and forestry. Carbon storage in land must be sensitive to drought and fire. What is the thinking on how to account for the potentially large drought and fire impacts on that land component, Rob?
Yeah, so that's a good question. That's one question that we worried about for a long time. So if I just think about fire, for example, well, we do effectively smooth the carbon stock change over time in the inventory. So you would have known a couple of years ago, bad fire season, if we just counted the flux from that CO2 from that fire, it would dominate everything else in the inventory. So, do we want to send a signal to the government that the best way to reduce emissions is to stop all fires in the future? It's not going to be very helpful. So we smooth out the emissions flux, but also the sequestration that follows, and we attempt to model a trend in the carbon stock change over time effectively. The other thing is that the government is in the inventory is responsible for the actual change in carbon stock over time. And so, yes, if the forest does not get back to its former self, then that's an impact on the carbon stock, and that will be reflected in the national accounts over time. But currently, the inventory is probably underestimating the amount of sequestration going on across the landscape. So, yeah, that cuts both ways. Yeah.
So if there was a systematic shift towards more fire and drought, that there would be a way to account for that, is what you're saying?
Yep, that's right. So we, of course, monitor the land coverage, the forest coverage and woody vegetation coverage across the country using satellite imagery. So up until now, we've used NASA Landsat series. We're moving towards the European Sentinel series, which is high resolution going forward. We work with the CSIRO to reshape the modelling on how that's all going to work in the future.
It might be worth noting also that the information I showed earlier was that there is a vulnerability of terrestrial carbon to at least to warming, aside from just a drought or fires. So we're seeing positive feedbacks in the long-term record of climate onto terrestrial carbon.
Yes, thank you, David. For those who've got a short question, we've got 60 seconds left. Type rapidly or pipe up. You can unmute yourselves and ask the question.
I have a quick question, Nathan.
Thank you, Roland.
Just following Joel's discussion, I wonder if Rob was able to say whether that recent top-down modelling reflected the variations that connect with those fire seasons. In some sense, it seems like your steady yellow line is because you smooth the data.
No, absolutely right, Roland. The satellite top-down will pick up those annual fluctuations. It will pick up the flux of the fire season, and we'll also pick up the rapid sequestration recovery. And in the imagery, we try and control for both of those things.
So that would be a good test of whether to believe Deng et al.
That's kind of a question to you as a parting shot. Maybe you can think about that, Rob. We've wrapped up. It's 11 a.m. I'd love to thank the speakers once again. Thank you very much for your presentations this morning. I actually think it's absolutely fascinating what's going on at the inventory level and from the global picture and from our ice cores. It's so important. Thank you, Rob. Thank you, David. And thanks to the audience for your questions and coming to the event. See you next year.
Thanks, Nate.
Thank you, everybody.